Welcome to Fundamentals of Cybersecurity, CSCI 150N. I'm your instructor, Peter Kurik, and this is Chapter 9, Network Fundamentals. In this chapter, you will learn how to identify the basic network architectures, define the basic network protocols, explain routing and address translation, and classify security zones. Now, most of you should have taken a networking fundamentals course before taking this class. It's part of your first semester of the degree. So some of this will be a review, or actually most of this should be a review if you've completed the course already. And so we're just going to breeze through this as quick as we can. This is the outline for this chapter. As I said before, I don't want to go into too much details in the stuff that you should have had in your Fundamentals of Networking course. But we will touch a little bit on each one of these topics. Networking architectures, network topology, network protocols, internet protocol, IPv4 versus IPv6, packet delivery, security zones, tunneling, and storage area networks. So there are many types of network architectures. Anything from LANs, which are local area networks, which you might find within a building or maybe a couple buildings, to wide area networks that spread coast to coast and from country to country. We also have campus area networks, which are self-explanatory. It might be on a college campus with multiple buildings, or a business campus with multiple buildings interconnected. And then metropolitan area networks might be, for example, a bank that has multiple branches within a metropolitan area like Boston and some of the surrounding towns, all linked together. Then there's the internet versus the intranets. The internet is a group of interconnected networks, which is what most of us use every day, or we use a portion of it. When we go web browsing, we're just skirting the surface of what the internet really is. But it's interconnected networks through a bunch of backbones and separate services that are working together to create the overall network around the world. Intranet is an internal network. This is basically your LAN, or maybe your CAN or MAN, but it's a organization's internal network. SANs are storage area networks. They're basically networked disk or storage available to servers and systems on the network for users to store information. VLANs are virtual local area networks. So it's taking a local area network and dividing it up into smaller networks to segregate traffic. Client servers, basically, you guys see this every day when you browse the web. There are servers out there that provide services available to you, and you run a client piece of software in order to interface with it. So in a previous lab, we did FTP. We FTP'd to an FTP server using an FTP client. As I stated, web browsers, but there are other things as well. So a lot of times, companies or organizations have software that interfaces with a database or something of that sort. And then peer-to-peer, pretty straightforward. This goes all the way back to before there was peer-to-peer software like Napster, BearShare, and things of that sort. Peer-to-peer could be as simple as you just share out a drive or a folder on your computer for another person on your network to have access to. But it was made more popular across the internet using software such as Napster. So when we talk topology, think of it like with maps, topological maps. It's basically the layout, the physical layout of the network. In reality, there's three types of network topologies, and they are star, bus, and ring. Star consists of a series of systems that are connected to a single central point. As you can see in the top right diagram, all the systems are pointing to one hub. Note, it's a hub, it's not a switch. If it was a switch, it would be a part of the next one, which is the bus topology. So a bus topology is basically a single wire that goes by, kind of like a road, and each system is plugged into it like a house is on a road. So if you go down the street, houses and buildings are all interconnected in that road, but they're not all coming to a central point like in the star. They're all as you progress further down the road. And then there's ring, which is basically a giant loop, and the information travels around in a loop between the systems. So, for example, in the bottom right diagram, you see four computers or four systems that are linked in a loop. So let's say the loop is going clockwise, or the information or token, and it actually uses a token in order to grant each system on the loop permission to speak. So it passes from one to the other in progressive circular motion. So let's assume that this particular diagram is going in a clockwise position, and we're starting at the laptop, and they want to send some information to the printer that's at the 9 o'clock position on that circle. So the token comes around to that laptop, and when that laptop has its permission to speak, it sends its print job, and that information passes around clockwise, past the server, past the desktop, to the printer. And when the printer acknowledges receiving it, it continues to pass that information in a clockwise fashion. So in this case, that information goes directly to the laptop as its next stop. Then there's also mixed topologies. So what you might find in, let's say, for example, a campus area network, you might find that there is a ring network topology put between all the buildings on a campus. And then inside each building you'll have a bus topology. The important thing to note about bus topology is you can have a single switch, a network switch, and that's still considered a bus topology, because the way that it works, the information moves up and down, as opposed to in a star, the information comes in and then goes out in all directions. So in that star diagram, that's a hub. For those of you who have taken a networking course, you understand that hubs interact on the physical layer, the first layer, which we'll get into in a little bit, and switches work on layer 2 or layer 3, but mostly layer 2, which means it's a bus. So I like to explain network protocols as kind of like going to a hardware store. It really depends on what you're looking to do and where you're looking to do it. There's so many different protocols out there, and they're based upon the types of systems that are connected, and how they're connected, and why they're connected. So AppleTalk, straightforward. It's communication between Apple computers on their own network. Asynchronous transfer mode. Then you got Ethernet being probably the most common today. Fiber distributed data interface, Internet protocol, inter-network packet exchange, signaling system 7, system network architecture, token ring, that kind of goes back to that ring I was talking about on the last slide, transmission control protocol and internet protocol, and X25A. Now, there's a lot of different ones here, and we can get into a lot of detail on them. I wouldn't worry too much about it in this class, about all of these ones you haven't seen before. The biggest area we're going to concentrate in is on IP and TCP/IP. The big thing to understand is this protocol, these protocols, it's actually a suite of protocols. These protocols were developed because the government was looking for a way to have systems become interconnected and speak to each other, when all these other systems are creating proprietary means of talking, and there's others that's not on here, like DECnet and stuff like that. When they are making proprietary ones for their own systems to talk to each other, the government was looking for a way to create inter-system communication independent of the platform that it's running on. And so really, this is a product of government spending and military spending, the creation of the Internet. So network packets, most of the time, different protocols might call them slightly different things, but ultimately what they're talking about when they break up information for transmission down a medium of some sort, they're talking about packets. Each protocol has its own definition of a packet, dictating how much data can be carried, what information is stored where, how the packet should be interpreted and by another system, and so on. Maximum transmission units, that's basically how large is the packet going to be. And packet fragmentation, how is the packet chopped up when it's too big, when the information is too big for a single packet, and how is it reassembled? Is it put together, or is it sent sequentially? And if a packet goes missing, does the information go missing? As I stated before, there's lots of different protocols that are out there, but for the purpose of this course, we're going to concentrate on the Internet protocol, mostly because it's what's being used for interconnectivity, so therefore it provides the largest footprint for some kind of a security incident to happen in it. The Internet protocol itself is not a single protocol, but a suite of protocols. There are differences between the two versions of the protocol currently in use, which are version 4 and version 6. Because the Internet Protocol is used for organizations to connect with other organizations and share information around the world, a security professional must understand how these various TCP/IP protocols operate. For example, if you're looking at a packet capture of suspected port scan, you need to know how normal TCP and UDP traffic works, so you're able to spot malicious traffic. The most popular IP protocols are TCP, UDP, and ICMP. So let's look at TCP versus UDP. TCP is Transmission Control Protocol. It's a connection-oriented protocol and offers reliable and guaranteed delivery of packets. And UDP is User Datagram Protocol, a connectionless protocol with no guarantees of delivery. These two are the workhorse of the Internet. TCP, as it stated, is connection-oriented. So in this particular case, with the diagram on the slide, the computer reaching out to the server sends a SYN packet saying, "Hello, I'm over here," and the server sends back a SYN ACK package saying particularly, "Oh, I acknowledge you're here. I'm here." And then the desktop or the user sends back a final packet saying, "Oh, okay, I see you're there too." And once that's done, they've established a connection, and then all continuous traffic after that continues to be validated, so they know that the transmissions are being successful. So if any packets go missing for whatever reason, there's an interruption, it'll acknowledge that it's missing a packet, and it'll send another copy of that same packet to complete the information. User Datagram Protocol, on the other hand, is connectionless. So in other words, there's none of this acknowledgement back and forth that, yes, I see you, yes, I've received your packet. Instead, it just says, okay, send me your information, and it just keeps sending the information. And if a packet gets dropped, well, it's lost. So TCP is going to be used for something that is very important, that you can't afford to miss any information. So that would be maybe email, your file transfers, things of that sort, where you need to have integrity and a validation that the transfer was completed successfully and the data was properly received. UDP is for something that does not necessarily need to prove that it's been properly received, and you'll see it on things like streaming video, streaming audio, things of that sort. Something where if a packet is lost, a piece of information is lost, the overall service is still okay as long as the bulk of it gets through. The third popular IP protocol, ICMP, or Internet Control Messaging Protocol, is a control and information protocol used by network devices to determine such things as remote network availability, the length of time to reach a remote network, the best route for packets to take them traveling to that remote network, and things of that sort. ICMP also can be used to handle the flow of traffic, telling other network devices to slow down transmission speeds if packets are coming in too fast. And you'll see quite often when you're doing things like enumerating a network, this is the protocol that you're doing. So IPv6 versus IPv4. So far, most of you have experience with IPv4. We used it in our labs so far. We've set up each of our virtual machines using IPv4 addresses. And it is the most common in use because it's what's been around for a while. It uses a 32-bit address space, and the biggest issue that we've run into with IPv4 is there's just not enough addresses for each person on this earth, let alone all the different interconnected devices. So think about in your home how many connected devices you have just for you or your family. So for example, I have a family of 6 children and me and my wife, so that's 8 of us, and we use probably 16 to 20 IP addresses within our home for the various devices that we have. So we average about 2.5 per person in the home. So when you count the number of devices that are out there, if there's not enough IP addresses for one address for every person on this planet, there's not going to be enough for all the devices that are out there. So the solution was to come up with IPv6, which had a 128-bit address space. And as of right now, the address addressing space has over 1,500 address spaces per square meter of the entire Earth's surface. That's more than enough for at least many I wish I could say hundreds of years, but probably for at least the next 100 years, unless literally every single device and piece of equipment that is owned has an IP address of itself. This is one of the immediate implications, where you can use a scanner to search all addresses for response for IPv4. So if you were to do, let's say, an Nmap of a network, doing the same in IPv6 will take significantly longer. So for example, a 1 millisecond scan in IPv4 equates to 2.5 billion years of scanning in IPv6. In theory, the 128-bit addressing space of IPv6 will express 3.4 times 10 to the 38 possible nodes, and that's quite a bit. The IPv6 addressing protocol has been designed to allow for a hierarchical division of the address space with several layers of subnets to assist in the maintaining of both efficient and logical address allocations. One example is the embedding of the IPv4 address space into IPv6. This has an intentional effect of simplifying the backbone routing infrastructure by reducing the routing table size. So that's one of the big issues with V6, is because of the way the addressing space is done, routing becomes an issue. So using IPv4 is still going to be around for a while in order to reduce routing table sizes, at least until there's a huge significant improvement in routing capabilities in the processing of routing tables. First, for just honesty and disclosure, I myself am not an IPv6 expert. I've been around IPv4 for some 20 years, so I'm very familiar with it, very comfortable with it, and I'm still learning and trying to do a deeper dive in IPv6 myself. It was introduced, or it did introduce the Network Discovery Protocol, which was useful for auto-configuring of networks. It can enable a variety of interception and interruption threat modes. A malevolent router can attach itself to a network and reroute or interpret traffic flow. IPv6 is designed to be secure from sender to receiver, with IPsec available natively across the protocol, as opposed to an IPv4 where you have to create an IPsec tunnel yourself. Virtually all the network equipment you will rely upon will be dual stack capable these days, meaning that they can operate in both IPv4 and IPv6 networks. So really you're going to learn is in your Cisco networking classes. IPv4 is the core of what they do. However, I think that the courses is starting to introduce more and more of IPv6. At least on my last exam for Cisco, there seemed to be a lot more questions on IPv6. So when we talk about packet delivery, we talk about how does a packet get from sender A to receiver B. So it can really be divided into two sections, local and remote. Local being on the same network segment on the LAN, and remote is anything off of that local network segment. So Ethernet is common for local delivery, while IP works for remote delivery. Local packet delivery applies to packets being sent out on a local network, being that same wire, that bus we were talking about before, or in a star from that central hub, while the remote packet delivery applies to packets being delivered to a remote system, such as across the internet, or even onto another subnet within your same network. Ultimately, packets may follow a local delivery, remote delivery, local delivery pattern before reaching their intended designation. The biggest difference in local versus delivery is how the packets are addressed. Network systems have addresses not unlike office numbers or street addresses. Like I was talking about before, that bus is a street. And before a packet can be successfully delivered, the sender needs to know the address of the destination system. I mentioned early on that Ethernet is the most widely implemented Layer 2 protocol. Ethernet is standardized under the IEEE 802.3, and it works by forwarding packets on a hop-by-hop or hop-to-hop basis using MAC addresses. Layer 2 addressing can have numerous security implications. The addresses can be poisoned, spanning tree algorithms can be attacked, VLANs can be hopped, and more. You can spoof a MAC address. We do it every day when we're running our VMs. If you take a look under the network settings, you can set a MAC address for the network card within the VM, and you could do it for the actual physical system you're on if you wanted to. but that's just an example right there. Ethernet is a common attack vector. It has many elements that make it useful for from a networking point of view, such as broadcast nature and its ability to run over a wide range of media. So local packet delivery on a network, such as an office, LAN, or something of that sort, usually works by sending the information to the destination hardware address or media access control address, MAC address. Each network card or network device is supposed to have a unique hardware address, so it can be specifically addressed for network traffic. So we're setting aside spoofing in this particular case. MAC addresses are assigned to a device or network card by the manufacturer, and each manufacturer is assigned a specific block of MAC addresses to prevent two devices from sharing the same MAC address. MAC addresses are usually expressed as 6 pairs of hexadecimal digits, such as 0007, E9, 7C, C8, 8AA. In order for a system to send data to another system on the network, it must first find out the destination MAC address. Once it has the MAC where it's sending it, the information is sent along the wire or the media to the system. So, depending on the topology, it will determine how that packet is received. So let's assume a ring topology, and you looking back at that laptop with the laptop going to the printer. The packet using the MAC address would first go to the server. The server would compare the MAC address to its MAC address. It doesn't match. It sends it along the way. Then the next one, the desktop, would look at the MAC address. Doesn't match its, passes it on. It reaches the printer. The printer says, "Hey, that's my MAC address. I'll take that packet," and it does so. The same thing happens in a bus topology. Depending on the physical the device that's being used, but on a bus topology, the switch it goes one step further. The switch learns MAC addresses of the devices on each one of its ports, and does some routing locally by saying, "Yep, this MAC address matches the person that's at the end of this port, so I'll send it out this port." Now, if it does not match any of the addresses that it knows, the switch will send the packet down all the ports and wait to see which port accepts it, and then it will record that one for the MAC address for future use. When it comes to the star topology, because it's a hub and it operates on layer 1, the physical layer, the same signals are sent out the ports to all of the devices on the network at the same time. So when, let's say, the laptop sends a packet to go to the printer, the server receives it, the desktop receives it, and the printer receives it all at the same time. And it's just a matter of which one responds. Those that are not matching the MAC address just totally ignore the packet. It just gets dropped at that end. So thus far, we've just talked layer 1 and layer 2 of the TCP/IP stack on how networks work. So layer 1 being your star topology with a hub, layer 2 being your bus or ring topology using Ethernet as a means of communicating and MAC addresses. So what happens if the device you want to talk to is not on the local network? Let's say the printer you want to print to, you'd say you're in New York City, and the printer you want to print to is in Los Angeles for your partner who's working out of the LA office who needs a printout. How do we do it? How does it communicate across the distances onto different networks? That's where layer 3 of the protocol stack comes in, the internetworking layer using the internet protocol in the IP address. So the remote packet delivery is usually accomplished using internet protocol addresses. Addresses are 32-bit numbers that usually are expressed as groups of 4 numbers. In order to send a packet to a specific system on the other side of the world, you have to know the remote system's IP address. Storing large numbers of IP addresses on every PC is far too costly, and most humans are not going to be good at remembering a collection of PCs. So there is a protocol that works with IP called DNS, so Domain Name Service Protocol. So basically, that's where your www.google.com comes in, because the reality is you might not remember that 8.8.8. whatever is one of their search servers. And then there's DNSSEC, which is the cryptographically signed version of DNS. has been created to reduce spoofing. So as we stated, the IPv4 uses 32-bit numbering scheme or 32-bit addressing scheme, which represents as 4 groups of 8 bits each, called an octet. You will usually see the IP address expressed in 4 sets of decimal numbers with dotted decimal notation. So, for example, here it's 10.120.102.15. Of those 32 bits in an IP address, some are used for the networking portion, and some are used to identify specific hosts. So it really comes down to the specific network you're on, and we're going to get into that in a moment. Subnetting is the process that is used to divide these 32 bits into IP addresses and tell you how many of the 32 bits are being used for networking ID and how many are being used for your host ID. Where and how you divide the 32 bits determine how many networks and how many host addresses you can have. To interpret the 32-bit address space correctly, we must use a subnet mask, which tells us exactly how much of the space is the network portion and how much of it is the host portion. So looking at IP addresses and subnetting, the first example of a subnet, we were just talking about masking. So you see a subnet mask where it's, let's say 255.255.0, and with that, what that means is that when you translate it out into ones and zeros by octets, as you can see here, the subnet mask is all ones for the first octet, the second octet, and the third octet, and then all zeros for the fourth octet. And then when you look at the IP address, translating that into binary as well, what you do is you actually match up the octets. So everywhere there's a 1, whatever the number is in the IP address remains the same. So it's either, in this particular case, we have all 1s for the first 3 octets, so all of the portion of the bottom, the IP addresses, stay the same as well. And then the final octet being zeros means that that's the area where the addresses can change. So that's basically defines to you what the network is. In this particular case, the 10.10.101, the network is 10.10.1.0. So anything in that last octet is accepted as a valid address. The only exception to that rule would be the last IP number that's available in that is reserved as a broadcast one. So, for example, 255 being the last number in the 10.10.10 would be your broadcast address. Now, subnet masks do not have to be 255.255.0 all the time. They could be 255.255.0.0, and they could be 255.255.254. So let's taking a look at 254, which would be the last one in that subnet mask just before the dot. It now becomes a 0. That means the last bit in the bottom IP address is changeable. So seeing how it's a 0 now, because it's 1010 for that octet in the IP address, let's assume that now with the subnet mask being a 0, that means that last 0 in that third octet for the IP address can be changed either to a 1 or a 0. So that what that would mean is that the IP space for that subnet would be a 10.10.10.0 through 10.10.11, because that 0 can become a 1 as well, dot 255. So all those spaces could be available if you needed to create a network with more than 254 possible devices on there. Now, looking at public IPs, and what we mean by public IPs, these are IPs that can be routed. So we were talking about going from New York to Los Angeles. That means that it can span the internet. So public IPs are routable IPs, and they have what we call Class A, Class B, and Class Cs. And so really it's just a matter of how many hosts do you expect to have. You can purchase the rights to the IP addresses within a particular range. So for example, let's say the federal government, with the number of systems that it has, could buy an entire IP range of, let's say, an entire Class A, theoretically, if they wanted to, and then subdivide it. So in here, the subnets are available is from 0.0.0.0 to 126.255.255.255. So let's say they want to buy the IP space for 125.0.0.0. That would be Class A network. Class B is hinged around the second octet in the IP address. So it's reserved for IP subnets of 128.0.0.0 to 192.255.255.255. So if I want to purchase or get the rights to IP space within a Class B network, it could be, let's say, IP address 129.1.0.0. That would be my network space. Then there's Class C, which is really limited to just about 253 hosts. If you needed more than that, you would have to go up to a Class B. And on that network, it would have a subnet mask of 255, 255, 255.0, or you can actually divide that into smaller ones below a Class C. But in this particular case, we'll limit it to this. So the IP ranges for subnets that are Class Cs start at 192 and end at 223.255.255.255. So if I want to buy a Class C, rights to a Class C, I could get, let's say, network 193.1.1.0. So all the last octet I could have for systems. So allowing for a router and everything in that space, I'd have about 253 systems in there. Then there's private IPs. These are specifically IPs that are not routable. So you can create a private internal network using Class A, B, or C IP addresses using what's known as private IPs. These are IPs that are not routable through the internet. So if you use one of these IPs, it just won't go anywhere. So it starts off with a Class A being 10.0.0.0 to 10.255.255.255. Next, there's Class B private internet IP space of 172.16 through 172.31. And then finally there's the Class C, which most of us have seen in our labs, of 192.168.0.0 through 192.168.255.255. So none of these IPs will be routable. And then there's a fourth one that's kind of interesting. It's the automatic private IP addressing. It's seen in Windows. It's those times when you've booted up Windows and you can't seem to get a network address for whatever the reason is. It's usually a misconfiguration, or the wire's not plugged in, or you've turned off your wireless if you're in a wireless environment. You'll see a 169 IP address. This is what it is. It's an internal private, automatic private IP address. So a subnet network address is basically when we talk about a network. If I wanted to set up a Class C using a Class A that we own, and I want to talk about the subnet, it usually ends in a 0. So if I want to say, so the subnet that I want you to put these computers on is on the 10.10.10.0, it means all of their IP addresses would begin with 10.10.10, and then whatever they're assigned for that last octet. And then a broadcast address, I think I mentioned this before, is usually the last address in the address space for that particular subnet. So, for example, we just talked about 10.10.10.0 being the subnet that's available. Its broadcast would be 255 as the last octet. So, we mentioned that we are running out of address spaces in IPv4 addressing space. Before the IPv6 was available, there was a solution that was put in place to help with the limited address problem, and that was network address translation. And one of the unique things about network address translation, or NATing, is that not only did it help with the IP address space issue by reducing the number of public IP addresses that were needed, but it also created a kind of a plus on the security side too. We'll get into that in just a second. But to compensate for the lack of IP spaces, we use NATing. It translates private non-routable IPs that we just discussed into public IP addresses, and there's 3 different ways that it does it. Usually, the NATing device is a firewall or a router that's been configured to do the network address translation. So the different types or approaches of network address translation or NATing are static, dynamic, and port address translation. Static is pretty straightforward what it means. It maps an internal private address to an external one. It's usually the same address every time, so you know exactly how it's going to translate. So for example, you might have an internal web server that translates to an external IP address, and it's always kept that way. So the traffic coming to the external IP address is translated back in through the firewall or the router directly to that web server. Then there's dynamic NATing. This is where, once again, you're mapping internal private IP addresses to a series of public IP addresses, and it's changed. It's a pool of IP addresses that's available, and it's whatever address is currently available is what's used. In both these schemes, though, static and dynamic NATing, it requires that you own a number of or more than one public IP address if you're going to have more than one system be NATed across the firewall or router. The third option is what was used to overcome that issue. So, for example, if you want to own a business and only have one IP address instead of 100 IP addresses, you want to use port address translation. So what this does is allows different internal private addresses to be shared to share a single external IP address. Devices perform a PAT and replace the source IP address with the NAT IP address, and replace the source port field with a port from an available connection pool. Port devices keep a translation table to track which internals are using which ports, so that subsequent packets can be stamped with the same port number. When response packets are received, the PAT device reverses the process and forwards the packet to the correct internal host. PAT is the most popular version of NAT, and a good example of this is probably how most of you have your home set up. If you have a cable modem or a DSL modem or some kind of internet service where you're sharing more than one device, you're probably using PAT because they're only going to give you one IP address. It's just Comcast or Verizon or whoever your service is only has a certain number of IPs to give out, and they're not going to give out multiples to a bunch of residential users. So security zones are really just dividing up your network based upon the priority of trust and the value of the systems that are within each of the zones. The first 3 are typical on most firewalls, and the second 2 can be added. And if you don't have a firewall, you can build them inside your router based upon subnets and VLANs. Demilitarized zone is an area of semi-trust. These are systems that you trust because they're your systems. However, you also have to take some protective cautions against because they have exposure to the outside world and could be potentially compromised because of that. So this is where you might have your database that is a public-facing database. It might be where you have a web server, FTP server, things of that sort. But your valuable data should be inside your intranet. This is your trusted zone. This is where you should have the highest level of security to get through and not allow a lot of outside to come through to it other than something that might have been initiated from the inside using like a stateful firewall. The internet is the Wild West. You assume that there is no trust whatsoever on any system outside of your firewall in the internet zone, because you don't know who's running it. You believe Google is being run by Google, but if it's being spoofed, you don't know that for sure. Extranets are kind of a partner network, maybe its own security zone, similar to a DMZ. So let's say you're working for company A and you have a partnership with company. You might put some systems in an intranet that allow both companies to share access to those systems without giving them full access to your intranet, or without being in the DMZ, which exposes us out to the outside world. And then flat networks. This is a concept that some organizations are going to now. Basically, what they're looking to do is do away with the hierarchy and flatten out the network more in the idea of providing better security. The book explains it a little bit, but I wouldn't worry too much about it. I have not seen much of this in the business world right now. So we talked about the three primary zones that you see in most places, which is the demilitarized zone, DMZ, intranet, and internet. So in this diagram here, it goes one step further and it starts talking about enclaves. So as you can see, you have your internet, your ISP network with a firewall, followed by your DMZ with another firewall. And then inside that firewall, you have your intranet. Well, the intranet can be divided into what they call enclaves, which are separated areas where only certain computers can have access to it, even internally. So that might be considered an enclave. So it's multiple sub-networks within your intranet. So in this case, in the diagram, you have your end-user terminals are an enclave. You have the high-security data center is its own enclave. Meanwhile, the database cluster is not secured by a firewall. It's not separated from the rest of the network, so it's not considered a enclave. You got your application servers that are out in the intranet, but not behind any firewalls. You got your management server, which is behind its own firewall, and your DNS server, which is behind its own firewall. So we talked about enclaves and how they separated out. For example, in the previous one, terminals in its own enclave and the high security data clusters in its own, and that was done by firewall and routers. But you can also do what's called VLANs, which allows you to separate out traffic so that you don't have traffic intermingling that doesn't need to work together. And it also allows two different locations to act as if they were next to each other. So in the diagram below, you see that there's the green line, which is the VLAN 10 for accounting. You have two people on two different floors who are accounting together, and to them, their traffic looks like it's on the same network segment, and it doesn't have any other traffic intermingling with it. So, for example, they might have an IP subnet of 192.168.10.0, and then the red line there is the VLAN 20, which is marketing, so all of their traffic is intermingled together, not touching accountings, and they might have an IP address scheme of 192.168.20.0. There are many. It has many of the characteristics of a wired LAN without having to wire individual LANs for each of these departments. So they'll share the same switch, and the ports would be assigned to the specific VLANs that they're assigned to. Segmenting out traffic is actually a good way to add to some security, because you don't need to have different departments mingling their traffic together and maybe capturing some traffic from another department if, for example, a computer becomes compromised. Previously, when I started talking about the routable protocols and routing traffic, we were talking about an office in New York and an office in Los Angeles. One way that you could do it is by tunneling. Obviously, the other is to just let the packet pass through the internet as it is, but it wouldn't be too secure. So what is tunneling? Tunneling is a method of packaging packets so that they can traverse a network in a secure and confidential manner. Tunneling involves encapsulating packets within packets, enabling dissimilar protocols to coexist in a single communication stream, as in an IP traffic routed over a asynchronous transfer mode network. And then tunneling can also provide significant measure of security and confidentiality through encryption and encapsulation methods. The best example of this is VPN that is established over a public network through the use of a tunnel. So, for example, the New York, in this case the picture shows New York and Boston, but either way, New York and Los Angeles, New York and Boston, however it's done, it creates a virtual tunnel. So it almost seems like they're on the same network, but in reality they're crossing over this space in the internet, and the rest of the internet can't read it because the packets are encapsulated and encrypted in using an IPsec tunnel or using some other VPN technology. So the book rounds out the chapter talking about storage area networks, which are systems which provide remote storage of data across a network connection. The design of a SAN protocol is such that a disk appears to actually be on the client's machine as a local drive rather than attached storage, as a network attached storage device. This makes the disk visible in disk and volume management utilities and allows their functionality. So in Windows, if you take a look at your Drive C under disk management, if you had a SAN disk share available to you, it would look like, just like it would with C, you would be able to format it and provision the space on it like any other hard drive was attached to your system. And some of the common SAN protocols include iSCSI and Fiber Channel. You'll see both of these in NetApp if you're using NetApp as your SAN. I wouldn't worry too much about it for the purpose of this class. Just understand that when they talk storage area networks, they're talking about the capability to provide a drive to people as if it was a physical drive, even though it is located across the network. I'm your instructor, Peter Keurig, for Nashville Community College. Thank you for watching.